All right, so here we have a system where y of t is equal to x of 2t, right? So y of t equal to x of 2t. So this is a time-scaled version, right? The output is a time-scaled version of the input, right? We compress the signal by 2 times. So is this system time invariant or not? Right. So how many of you think it's time invariant? So how many of you think it's time varying? Right? It's not time invariant. So how many of you are not sure? Okay, nobody wants to raise their hand. Okay. Okay, so this is not time invariant. Right, very good. It's time varying. It's time varying. Yeah. Okay, so to show that it's time varying, you just need to consider a particular counterexample. Okay. So here, the counterexample we're going to look at is the case where x of 1 of t is this square signal. Okay. So, right, if you insert a signal x of 1 of t that looks like this, then the output would be a time-compressed version of the input by 2 times, okay? So suppose that this is 2, then it will be compressed to 1, right? So this is just a time-scaling system. Right. Now suppose we consider a time-shifted version of x1. Right, so suppose we let x of 2 of t be x1 shifted by 2 units of time. Okay? So originally x1 is here. x2 is shifted by 2 units, which becomes this. Okay. So if you insert x sub 2 of t into the system, your output will be a compressed version of x2 by 2 times, okay? So this is compressed towards the origin, right? So originally the signal is from 0 to 4. Now it becomes from 0 to 2, okay? Now, if you compare the two, you'll see that y sub 2 of t is also a time-shifted version of y1, but it's only shifted by 1 unit time, okay? It's only shifted by 1 time unit, but if you want this system to be time invariant, it needs to be shifted by 2 time units, right? So this is equal to y sub 1 shifted by 1 time unit, which is not equal to y sub 1 shifted by 2 time units, okay? So hence the system is time varying. Okay, so any questions here? Okay. So if not, let's go to our last property, which is linearity. Okay. So what does it mean for a system to be linear? So basically, a system is linear if it possesses the superposition property, okay? And what is the superposition property? Right, so it can be described by the following 2 conditions here, okay? So what this is saying is that, suppose that you have 2 signals, x1 and x2, and their corresponding outputs are y1 and y2, okay? So suppose that the response to x1 is y1, and the response to x2 is y2. Okay. Now we say that a system is linear, or that it satisfies the superposition property, if the response to the addition of two inputs is equal to the addition of their corresponding outputs. Okay? And secondly, the response to a scaled version of the input is a scaled version of the output with the same scale. Okay? With the same scale. Okay? And this scale here, in general, can be complex. Okay? All right, so a system is linear, or that it satisfies the superposition property if x1 plus x2 leads to an output equal to y1 plus y2. Okay? And this is called the additive property. And that the response, and that the input a times x1 leads to an output that is equal to the same a times y1. And this is called the scaling or homogeneity property. Okay? Now, you can actually combine these two conditions and write it more concisely as the following, right? So basically what this is saying is that if you have a superposition of signals x1 and x2 scaled by a and b respectively, then the output will be the superposition of their corresponding outputs scaled by the same values a and b. Okay? Right, so if ax1 of t plus bx2 of t yields an output that is equal to a times the output of x1 plus b times the output of x2. Okay? So you can also, right, if you've taken a class on linear algebra, you can also say that, this is a linear combination of x1 and x2 with the linear combining coefficients a and b, right? So a linear combination of the input yields a linear combination of the corresponding output with the same linear combining coefficients. Okay? And this holds true both in continuous time and in discrete time. Okay. So if this superposition property holds for two signals x1 and x2, it must also hold for three signals x1, x2, x3, and also for four signals x1, x2, x3, x4, and so on and so forth. Okay? So in general, if you have xn equal to if you have xn that is equal to a linear combination or a superposition of these different input signals, then the output yn should be the same superposition of the corresponding output signals. Okay? And here, yk, right, is the corresponding input, corresponding output of the input xk. Okay? So again, in general, if you have a signal xn that can be written as a linear combination of different signals xk with linear combining coefficients ak, then the output yn, right, will be the linear combination of the corresponding outputs with the same linear combining coefficients. Okay. Now this leads to an interesting consequence, right? So consequently, suppose you have an input that is 0, okay? So what is the output to an input 0? Are you able to infer the output of an input 0, okay, if it is a linear time invariant system? I'm sorry, if it is a linear system. Okay. So the answer is yes, because when you look at 0, right, this constant 0, you can view it as 0 times some input xn, right? So by the superposition property, the output must be the same 0 times the corresponding output of xn, which we denote by yn, and this is 0.